This early morning, we appreciate it. I'm actually really excited to be here. So it turns out if you organize an event and do a technical talk, it's quite a challenge. So I'm really glad we made it. It was not an early night last night, but I think we're in good shape. Huh? Okay, so first off, does anyone here have these kinds of smart lights at home yet? Can we see a raise of hands? Also, there's maybe a quarter to half of the room here. This is very interesting. Hopefully, you will have some new tricks up your sleeve after our talk. Okay, so first off, who are we? My name is Tom. I'm one of the organizers of the camp here. I'm a firmware engineer at Ultimaker, and I have a little company that makes quirky electronics gadgets. I'm here with my long-term friend, Gillet.
Yes. Hi, my name is Khaled Nassar. I am a security engineer and an internal blue team, so I do incident response. I'm quite an avid CTF player. I've been playing for about 10 years with my CTF team, Spotless. And I do quite a bit of stuff in my free time, including projects such as this. I'm going to move to Tom now to introduce the rest of the first talk.
All right, so what are we talking about today? We're talking about these kinds of smart IoT lights. First, we'll do a quick introduction of how we dove down the rabbit hole that we are in now, how we got to this. Then we'll talk a bit about the initial revision of hardware that we found, then a big revamp with a new type of chip where we found some new things. And finally, we'll show you a vulnerability that we found out is running on millions of devices all over the world that we use to break free of internet-connected servers and run these devices locally only inside of your own network. Hopefully at the end there will be some room for questions, but we'll see how the time pans out. All right, so starting with our inspiration. In 2019, Dutch hackerspace Hack42 called up all the troops and said, we found these devices at Action, a local store. They're a power plug that connect to your Wi-Fi, and you can hack them to run locally. You can run whatever firmware you like on them. And they organized this session to hack these devices together. They put it up on their wiki. You see it on the right. They found that there's this tool called Tuya Convert that you can use to break free these devices of the firmware that they came with and instead flash your own on it. And this Tuya Convert, an open source tool, turned out to be based on research from CCC 35C3 by Michael from vTrust, who's actually sitting right here in the room. So he found a really cool bug that allowed you to take control of the device and flash your own firmware to it. And how did it work? So the device connects to the server of the manufacturer. It has a sort of handshake where it sends some information, including this thing called the PSK ID. And then it starts encrypting the connection with TLS PSK, pre-shared key. This pre-shared key, though, it was derived from the PSK ID that got sent. So it sent to the server all the information you need to figure out how to encrypt and decrypt the data. And so using this knowledge, you can actually get rid of the whole vendor server, act like you're the server, and take control of the device. And this is the trick that was used to flash custom firmware then. And so when we bought some of these lights for our home, we figured, okay, we can just use this Tuya Convert, and our entire home will be cheaply filled with smart IoT devices that we can do fun stuff with. Wrong. At some point, Tuya, the manufacturer of these devices, and millions of devices like them, They manufacture them white label for thousands of manufacturers. They changed their firmware. They patched this stuff that Michael found, of course. And from that point onwards, the pre-shared key was no longer derived from stuff that you could see publicly. Instead, it was seemingly, we think, generated randomly at the factory, flashed to the device, unique per device, and you could no longer see it. Shit. So now what? We got a whole bunch of these lights, and we cannot do anything with them other than let them happily connect to their servers of Tuya. So we figured, okay, if they're not vulnerable anymore, we simply have to make them vulnerable again, right? How hard could it be? And so there's a couple of options, we thought. One, we can obtain the PSK again, either leaking it or changing it to some value that we want. Or we can try to downgrade this version 2 of the protocol back to version 1 that was vulnerable, and then use Tuya Convert again. Or, if all else fails, we just get code execution on the light bulb, right? Well, you can guess where we ended up. So first off, we started with this initial hardware revision of them. This was from light bulbs we bought in 2019, I think. It contained the ESP8266 chip, a very popular microcontroller that has Wi-Fi. Super popular, and because it's super popular, there's also a whole bunch of tooling that you could use. We could dump the firmware from these light bulbs using ESP-Tool, a common tool for handling Espressif chips. You get a raw binary flash dump from that you can then load into a tool called ESP-Bin2Elf. That gives you an ELF executable image, which you can load into Ghidra using an extension, a module for Extensa architecture. Then you analyze the firmware you dumped, and you find a whole bunch of functions that are not annotated. They don't have symbols, so you don't know what they do. There's a simple trick that you can use to get at least symbols for many common functions, which is you just compile a demo application using the Espressif SDK. You analyze that in Ghidra, and then you compare the footprints of functions with each other. So you have a list of functions on the right, a list of functions on the left, and you can map them. There's tools to do this, but of course we didn't know about it back then, so we made a simple one of our own. We mapped these functions and got a sort of lay of the land. We found out that Tuya, the manufacturer, runs FreeRTOS on these devices. In FreeRTOS, they have a whole bunch of tasks. One task, the init task, that starts all the other tasks. And two, to us, particularly interesting ones, a task called UDP receiver, which listens for broadcast traffic on the network, and a task called smart frame task that handles commands that you send to it via including this UDP receiver task. And on top of this, they have a bunch of drivers for controlling GPIO and PWM peripherals and this kind of stuff. All right, so now how do we get root on these things? We found that there's a bunch of keys used in this firmware. The PSK key that we talked about previously that encrypts the connection to the server. You see that in yellow on the slide. But also other ones, and this we did not know about before. So data inside of this TLS encrypted connection is encrypted and signed by something called the AUS key, which after you activate the device via their servers over the internet gets replaced by something called the SEC key. And all of that is separate from something called the local key, which you obtain after activation with the server. It's initially empty, and after activation, you can get it to then use the device on your local network without an internet connection. Well, we wanted to use it without connecting to the server in the first place, right? So our goal was to get ownership of these keys somehow without connecting to Tuya. And for this part, I will hand over to Gillet.
So, we've analyzed and reverse engineered the firmware for this particular revision for quite a while. We actually stumbled on a few vulnerabilities throughout our analysis. However, as luck would have it, we would not actually end up exploiting these particular vulnerabilities. So there's more later, of course, otherwise the talk would pretty much end here. But yeah, so we think these vulnerabilities are interesting. Nonetheless, we would like to share them with you. And let's start with the first one. So what you see in front of you on the slide right now is a function in the firmware. It generates a random string. You see it takes 3 parameters. The first one is completely unused. The second one is a character pointer. It's really a pointer to a buffer. And then actually the maximum length, which is essentially the length of the buffer itself. What the function does, very briefly, is it takes the current time. And do keep in mind these devices are set up without a real-time clock working. So essentially, this really is just a counter from the boot time of the device. It just keeps incrementing well, every second, sort of. And it takes that, it generates some index in it, and it indexes into this interesting string that's highlighted in red. This is kind of an artifact from Ghidra, because that's where we copied the code from, but this is essentially this really massive long string that is hard-coded in the firmware. And basically what this function does is it takes a substring of that, returns it, and calls it random. Now that's obviously not very random, but of course, you know, for a lot of things, yeah, you don't really need a cryptographically secure random number generator or something of the sort. So would have been fine if you maybe perhaps come up with a construction like this for other purposes. However, if you use it for TLS, then you have other sort of problems. What we ended up finding out is if you were to look at the traffic between the device and the cloud server, just zooming in here on the client hello message from the client to the server, you'll see that the random field that's highlighted in blue, and also in the dump, you see it bordered by red, is essentially pretty much the first part, like the first 30-something characters of that very, very long string. Now, in this particular setup, because they use TLS with pre-shared keys, this isn't actually much of an issue. We actually talked to a friend who did quite a bit of research on TLS, and we were wondering if this could be exploitable in the TLS PSK setup. However, turns out TLS 1.2 and up are actually quite resilient protocols, and this doesn't immediately lead to a vulnerability as far as we know. However, why we think this vulnerability is interesting is should they at any point switch to using cipher suites that actually utilize a key exchange mechanism such as Diffie-Hellman-Merkle key exchanges, using perhaps certificates for validating the exchange process, then this would immediately yield a man-in-the-middle attack, because now that you have the client random, which you can guess with relatively high frequency and figure out what the correct value is. If you just capture the first few handshakes between a client and a server, then you can just go ahead and derive the TLS pre-master key once, just keep reusing it over and over, and that's pretty much a win. We did some more analysis. Now, we found some protocols, as Tom mentioned. There were some function handlers that were handling messages from the network. Some of them were actually handling messages from devices on the local network. In particular, these messages were completely unencrypted, so we thought that they would be interesting candidates to look at the functions that parse and handle them, because, well, yeah, those are ones that we can easily reach. We don't need any keys to send messages to these handlers. And so we did, and we ended up finding 2 bugs there: a stack buffer overflow in the function that parses it, and a heap buffer overflow, and the same function but for a different message. For the stack buffer overflow, the function is implemented as a free RTOS task. What that really kind of means in traditional terms is it's a long-running process. It's essentially, in this case, an infinite loop that just keeps on running, waiting for messages to come in. And for every message, it just parses it, does some handling, etc. Now, we had control over the stack somewhat. It was a bug where we, as long as we are not writing null bytes, we can modify the contents on the stack at the location of the vulnerability. And that allowed us to overwrite the return address. Should be a win, right? We should be able to just go ahead and take control of the code flow and then perhaps do something useful. However, well, yeah, it's an infinitely running process. At no point does it ever return. We could not find a way to maybe trigger it into a fault mode that would have it do an early return or some such. And sadly, also analyzing the stack parameters and around it, we couldn't really find anything interesting that we could use to make it do something a little bit more. So essentially, we could just crash it, and that was pretty much it. For the heap buffer overflow, kind of a similar story. We could manipulate the metadata of the blocks that the heap allocator keeps track of for allocations and frees. We decided to study it a little bit, and we found out that Tuya has just modified one of the heap implementations that's provided with free RTOS. But so far we've done all of this statically, right? We have Ghidra open, we've got our decompiler, disassemblers, and we're just kind of analyzing code manually, going through it by hand. But when it comes to things like allocator misuse bugs, it's, at least in my experience, a bit more tricky to do that just by hand. Usually it's quite nice to see if you can get some dynamic analysis going, so some debugging, getting a bit of an understanding of what's actually happening in memory when you're doing all sorts of stuff. So we decided to take a little detour then, and somehow rediscovered a nice hardware hacking technique, which is if we just trigger the conditions that we want on the device, reset it into boot ROM, and then use ESP-Tool, the tool that was already there, we could actually get a really nice RAM dump of the contents of memory at the time we triggered this process. And turns out you can just take this RAM dump and overlay it onto your binary in Ghidra. It supports that, which is quite nice. And then you can kind of see, so in this particular screenshot, you actually see one of the blocks of the heap allocator, the heap allocator used. And you can kind of see the connections between them. So it's a bit more of a hybrid. You're not just reverse engineering code. You also get some data in there, and you can kind of see how this data relates to the instructions that act upon it. We went a step further, actually. So searching on the internet for if we can do on-chip debugging with the ESP8266 yielded a whole lot of no's. But there was one yes. There was one tutorial about using Visual GDB to debug applications on the ESP8266. However, we would have preferred to utilize just GDB and OpenOCD. Those are the tools that we're more familiar with. So what we did is we forked the Binutils GDB Extensa. That's actually been tailored for the ESP32, modified it just a little bit to get it to work nicely with the ESP8266, and got some help from some people on getting OpenOCD running properly with our debuggers of choice for the ESP8266. Now, this helped us a lot. We actually were able to debug what's happening on the chip as we're triggering the vulnerabilities and see how things progress and put breakpoints. Sadly, just one breakpoint. So it was a bit of a monkey jumping around with that one breakpoint. It was not a very nice experience. But it is what it is. We got somewhere where we didn't expect to. Unfortunately, as we analyzed it more and more, we realized that the conditions for that heap buffer overflow in the ways that we found that we could possibly abuse it would actually need us to be able to write null bytes in locations which are not at the end of that string, which we could have possibly been able to do. However, we really needed to do it somewhere in the middle just to get it to trigger writes just the right way. So unfortunately, this particular bug was not usable in this case. So, kind of wrapping up this stage of our research, we found a few bugs that, as I said, weren't easily exploitable. One of them actually didn't really apply at all, but we thought it was really cool, the TLS one. Should they ever move to some sort of implementation with key exchange mechanisms, then that would immediately yield an attack. We kind of rediscovered a nice technique, or at least we thought it was quite nice. We got debugging working. And more importantly, we learned a lot about Tuya Stack. This would actually kind of be the most critical point of our journey with the first revision of the devices, as it would actually help us a lot in the next stage. And speaking of the next stage, moving to Tom.
So a few months passed. We had no progress on the ESP, but still we were curious, of course. And one of us, I forget who, went to the Action, bought more of these lights, different types, and we got a bit startled because all of a sudden there was not an ESP8266 in there anymore, but a new chip, Chinese manufacturer, Beacon. We didn't know anything about it, a BK7231. And we thought, oh my God, has all of our research been in vain? Did they just swap out a new chip? Everything is different. So we went in search for a datasheet of this new mystery chip. We searched on Mouser and DigiKey, even Chinese LCSC. We could not find anyone supplying this chip and having a datasheet for it. Not on the Western internet anyway. Baidu to the rescue. So Baidu, a Chinese search engine, is used almost exclusively in China. Of course, when we searched there, we got a whole lot further. Some translations later, we got the datasheet for this chip. Inside of the datasheet, it's mentioned that there's an ARM9 core inside of a specific type. And that ARM9 core, that you can find on the Western internet very easily. From there, you can get the reference manual and see all kinds of things about the debug peripherals it has, what kind of memory mapping is inside. And this gave us a whole lot of information on how to analyze this new device. And what was even more interesting is what happened when you searched for this chip on the Western internet. Not for a data sheet, but just the chip name itself. We came to this very interesting looking GitHub repository. Do we now have an open source implementation from Tuya, the manufacturer of this device, for the SDK? Yeah, it turned out we did. They completely open sourced all of their stuff. The SDK, example applications that we found out are being used by manufacturers of these lights, almost exclusively. It's all there. Of course, some of the internals are in binary blob libraries, but because they're part of the SDK, you need to be able to link against them, which means that they need to have symbols, which means that now we can load the library into Ghidra, and we have a complete list of function names and this kind of stuff, structures, so that you can imagine this helps tremendously in reverse engineering. And so it did for us. One thing that's interesting is that they named this new real-time operating system IoT OS. And so we were curious to see if we would have to learn a different OS in our future endeavors, but luckily it ends up we do not. It's just free RTOS with some sauce of Tuya on top of it. So not only did we not lose progress, we actually gained a lot. The stack is still the same, but now we have the source. We have all the symbol names. We have a lot nicer time debugging because this ARM core chip supports a lot easier debugging than the Espressif chip does. It just has a JTAG interface you can connect to. And so now we dove in again. And for this part, I'll hand over to Gerrit again.
Right. So, as Tom mentioned, the SDK and the blobs in it actually helped us quite a lot. We thought, hey, we could get a really nice quick start on analyzing this particular new revision by just, well, looking at the SDK itself. So I started reverse engineering, sort of. It is mostly simplicated, easy to go through. The binary blobs that we found in the SDK. And because we've already seen quite a lot of what Tuya does, we've been familiarized with the protocols, I had a pretty good idea of, okay, what are the usual suspect protocols that have some interface to the outside world that we can perhaps control. So I started looking through these, and I stumbled upon this particular piece of code. It's kind of condensed from the original, of course, just for visuals. But essentially what this is a task definition for a FreeRTOS task that the device runs when you set it in a particular configuration mode. You do so by power cycling the device a specific number of times. This sets it in what's called AP mode, where the device essentially broadcasts an access point, and you connect to it with your mobile phone, and you have Tuya's app or any of their other rebranded apps on your phone, which has a nice UI. It tells you exactly what to do to get that device onboarded onto your home access point, with your home network. What this function does then is it actually listens on that AP network. It listens for UDP messages that the application sends. And what these messages look like, as an example shown on the right, essentially it's pretty simple. It's some simple format. It's a type length value around a JSON blob. Completely unencrypted. The app just sends that when it gets the parameters from you, the user. The first two parameters are the SID and the passphrase. That's your home network configuration parameters that it will use to connect. The last one is a token that it actually gets from Tuya servers, and it's essentially just used to get the device to initially authenticate with the server. So, looking on the left side, how it's being parsed, it's just using CJSON, a small library for parsing JSON in C. It's used quite heavily in embedded projects, as we've seen. So it just uses CJSON, takes that JSON payload, parses it, and then it gets the data and then copies it into some structure. So there's some global structure, so this LAN access point network config, and it copies the parameters in it. We noticed one particular interesting copy over here. It's highlighted in red. I hope you can see it. For specifically the token field from the token on the right, the AP configuration token, the copy process is slightly different than the other two fields. Why? Not sure. But what we saw is that the token length is first calculated as a C string, so it calls strlen on it, gets the length of that, and then uses memcopy to copy that much data that it just calculated with strlen into that field. Okay, could be okay, but there are no checks on it, but it depends on how big that field is. And do keep in mind that the JSON messages are not allowed to be more than 256 bytes, so it could still be all right. However, looking up, this is actually the structure that it copies into. That token field is only 64 bytes long. We can go up to 256 bytes. Okay, well, what that really means is we can set a token field that is much, much larger, or at least just larger than 64 bytes, and then we'll start overwriting fields in that global configuration structure that may actually yield something interesting. And lo and behold, there's something interesting, almost way too convenient, really. There's this finish CB, that's one of the fields in that structure. It's a function pointer, and it happens to be called immediately after our out of bounds write, our memcopy. So that's fantastic. So all we have to do is just have a token that is 72 bytes or, longer than 72 bytes, and it will start overwriting that callback function pointer. So now we have control over the program counter, which essentially allows us to jump wherever we want in the firmware. But all of this we've done so far on the SDK blobs. We don't really know if the devices themselves are vulnerable. We've tested them a little bit, kind of black box, by trying to exploit them, but it's a little unclear. So we decided the next step is to get firmware dumps. The plan here was to dump the firmware, analyze it, reverse engineer it in Gitter like we've done so far, kind of compare and figure out, okay, does this actually exist in the same way? Additionally, we also get to figure out which locations in the code are interesting. However, we really did not know much about this chip. So as Tom mentioned, documentation is scarce, if non-existent. So how are we actually going to dump the firmware? So turns out there is a serial protocol that this device implements in its bootloader that allows us to read Flash, read some of the device metadata as well. And do keep in mind that Flash is embedded on this device. It's not actually external, which is why this was a little tricky. The only problem is we don't really know much about this serial protocol besides that, it exists. Well, turns out we knew a little bit more. So Tuya had some developer documentation that actually explained for OEMs that would use their services, how do you flash your firmware onto the device, both using their own tools as well as using this very interesting binary called the BK7231 chip flashing tool. So we started looking around for information about this based on this newfound knowledge. And luckily, we actually ended up finding an open source project from one of Beacon employees, and Beacon is the company that makes these chips. And it's this tool that actually implements this bootloader serial protocol. However, not very luckily, the tool was quite unreliable for us. We really could not get it to work to read Flash at all. For whatever reason, it would just hiccup or something would go wrong, and we weren't exactly sure what's wrong with it. We tried to modify it, but that kind of didn't work out all too well. So we decided to use the information that we have from this tool and the fact that we have a copy of the bootloader in the SDK to both reverse engineer the bootloader so we can actually see what that serial protocol does from the horse's mouth, so to speak, as well as use the library that we found, the tool that we found, as kind of a quick guide point, because we can then just figure out, okay, what sort of artifacts do we really need to search for in the bootloader so we don't have to really go through the code in depth to figure out where we need to look for this part. So we spent some time on it. And after a while, we've figured out how it works. We decided to write our own tool. It's called the BK7231 tools. And essentially, it allowed us to now dump the firmware. But next step, we just have a flash dump. We actually need to analyze it before we can look at any code. So luckily for us, the SDK is open source, and this part of the part of the linking of the blobs together after compilation is available, so we could just go through it. What we learned is that there are two code partitions on Flash. The first partition is just the bootloader itself, the second stage bootloader after the boot ROM, and the second part is, well, what's interesting, the user application, or so they called it. The user application is essentially what we're interested in. There are other partitions as well, and they're defined by this user application. But of course, in very embedded software fashion, the code sections are encrypted, and by encryption we really mean obfuscation, because the the encryption key is just hard-coded in the SDK. So we had to deal with that a little bit as well. Now, of course, we just implemented all of that in BK7231 tools, so it just does the whole process now from dumping the flash from the device with that serial protocol to decrypting the code blocks and actually unwrapping their custom sort of format that they use both for on-chip, over-the-air updates. It's called an RBL format. So we did a little bit more reverse engineering around their binary tools that they had in the SDK. So now, armed with all of this information, it's now time to start making our bug a little bit more useful. So let's do a quick recall. This is actually what we had. We had the configuration message coming in, we had the token field, and if it's longer than 72 bytes, we would overwrite this function pointer. So here's an idea. We don't actually have control at all on the stack at the time of invocation here. However, there are some registers that are that point to data that we control, namely the data that's parsed in this JSON object. So hey, maybe we can write shellcode and just jump to it on the stack. You know, this usually works. Well, turns out that was not quite the case. This was quite surprising for us because the ARMv9 is a very old chip, and as far as we can tell, it doesn't have any memory protection units or any sort of memory management units. So there should be like almost all memory regions should be executable, but for whatever reason, this really did not work at all. So even though we have control flow redirection, well, we didn't really have much yet. But there are techniques to deal with that. So we could do return-oriented programming or call-oriented programming or some version of them, and basically reuse the code that is already in the firmware to kind of do our bidding. Now, we did actually end up figuring out something around that. We thought that, and from previous runs with the ESP version, we knew that there is a way to overwrite the pre-shared key through a call to the API, and then the device would pull that new key from the server and overwrite it in Flash. So we found that function, and we thought, okay, this is a really nice function that we could jump into. So this is a piece of code that's already on the device. And all we have to do is just massage the parameters a little bit, and if we just return to that function, it'll overwrite the pre-shared key for us, and we'll end up with a win condition. However, it turns out that this was really not sufficient. Overwriting the PSK worked. We did actually get it to kind of downgrade into the previous protocol that it had that Tuya Convert abused. However, the SDK is written such that it does not actually accept unencrypted traffic within the TLS connection, which the previous version did. So we kind of had to reassess what can we do here? What's our pathing to get this? So we actually did manage to overwrite the PSK. The downgrade doesn't work. Code execution, a little bit tricky still, but we can maybe find a way to overwrite the security keys, which turns out is exactly what we did. So we thought, okay, they have some function that they use to write this pre-shared key parameter and persist it to Flash. Perhaps we could just, you know, search for other functions that maybe use this function. So we started on this little journey for what's called gadget hunting, and a gadget really is just a piece of code that does something useful that we want to achieve. And in this particular case, we were looking for two gadgets. We were looking for something that sets the security keys that we can just jump right into and let it do our bidding, and perhaps one or more quote-unquote fix-up gadgets. And these just do simple tasks of moving registers about just to get things in the right order. We used a tool called Ropper to analyze the firmware. It's for the second type of gadgets. It's a tool commonly used in exploitation, also for traditional systems. So As we moved about, we actually ended up finding out one such nice target gadget, so that function that overwrites all the keys. We noticed that this WD GW base IF write was used to overwrite the PSK, and just by kind of cross-referencing back what sort of other functions refer to that function, we ended up finding this handy-dandy function that does not seem to be called at all by any tasks, but seems to exist for the purposes of writing these configuration parameters to the device in the factory through some serial protocol. It's pretty straightforward. All it does is it takes a JSON payload over serial, parses it, and then just uses it to overwrite the parameters in Flash. So this looked like a great and fantastic candidate for us to use. And since we already had a JSON blob that we actually sent to the task to actually exploit it, essentially this was just a matter of swapping some registers around because we already had a nice pre-parsed JSON object. And in order to do this swapping around, we have the fix-up gadgets, also trampoline gadgets on the side. As you can see, this one, it simply sets the first register R0 to the value of the register R7. I think in this particular case, it was the JSON object indeed. And then it pulls R3 on the third line from some other data section that we actually had some control over. So in this way, we could do some jump that does some register swap, and then from the register swap, we can go to a secondary location, which essentially should be our target gadget. And kind of putting everything together over here, we had the setup where we had the vulnerable function, call the fix-up gadget, does some register swaps, and then we end up in our lovely function that did all the work for us. Now, that's not quite over yet, so we're just moving to Tom here to explain what we did after that.
Yeah, so now we have an exploit. We can set the keys, but it's not usable for people aside from the two of us yet, right? So we built a small tool called Tuya Cloud Cutter. It contains all of this exploit toolchain steps, plus some additional things. So you can use it to override all of the keys, PSK, ASCII, local key, sec key. By doing that, it disallows the device from connecting to Tuya, so it's cut off from the cloud. It allows you to connect locally with this local key. And so you can use it in complete isolation on your own network. And then also you can use Tuya Cloud Cutter to write your own firmware if you like. If you're interested in it, check it out on GitHub. There's a link in the slides also. But I think now we should use the last final minutes that we have for actually trying to show you. I'm going to put this light bulb from Action into AP mode by flicking the switch 6 times. Gerrit is going to connect to it via his laptop. And then he's going to run the first step of the exploit toolchain. So it's blinking slowly now, which means it's in AP mode.
All right, now we have the exploit.
All right, so the exploit has run. I don't know if you can see it. It's all the way at the bottom of the beamer here. We put it in AP mode once again. This time to configure it to join a different access point that Gerrit has on his mobile phone, his hotspot. And then from there, we can connect to it using the local key to make it do something. And hopefully we can show you that it will do something. Of course, these kinds of demos are super dangerous to do on a camp like this. Huh? So this is all connecting over Wi-Fi to each other on a stage with, I don't know, 50 people here and hundreds around.
So we've got configuration messages now from the device. We know the exploit worked because we can actually see them. They're plain text, so we're doing the man-in-middle correctly. And now the device should be on our access point. So let's scan for it. We just need to figure out if it was onboarded correctly. Hopefully it is. And oh, I am on the incorrect network. Tends to happen on live demos.
So right now the bulb should be connected to Khaled's mobile phone. It's running a hotspot. He's connecting his laptop to the same hotspot. And then the laptop can send commands directly to the light bulb. If things work out, we'll see, huh?
Yeah. There we go. Found the device. Just need to get its IP address. We have a little script that would then use the local key that we've set on the device to actually make it do something a little bit more interesting, such as this. So we'll leave this running in the background. Oh. There we go. Right, now back to Tom.
All right, so in closing, we found a really cool bug that seems to be present in all devices containing this new chip, which we think is any device made by Tuya, millions of them since around 2020. We did a vulnerability disclosure to Tuya. They were really cool about it, really nice people, responded super quickly, and they gave us a bug bounty for it. We donated it to charity, to a foundation that teaches kids how to hack, which we thought was really cool. And for us, this was a first experience, or for me, it was the first experience of doing a vulnerability disclosure. Khaled did it before. So that was really nice. And one takeaway for us as well was embedded security is catching up. This kind of stuff we had with not being able to just send shellcode to the device and jump into it because of non-executable memory. It shows that steps are being taken. However, it's still far behind personal computing. So this makes it a really interesting target for us. And so our message is that it's still juicy to look into these embedded devices, because many of the tricks that have not worked in personal computing for quite a while now, they still work here. All right, and with that, we will leave you. We want to thank a couple of people, Yus, Blasti, Yilles, and VTrust for helping us along the way. If you would like to get in touch with us, our stuff is up there. And thanks a lot for listening.
Well, thank you so much. That was amazing. I'm not really a tech person, and I understood so much of it. We have 2 vacancies open at my school for computer science teachers, so if you're interested. Now, if there are any questions to them, there are mics in the middle. Please use them to ask a question, if you have one. No questions? Well, I think if you come up with a question, they're still approachable after the talk or somewhere around camp. And thank you so much. Another big applause, please.